Welcome everybody, Coffee with Caleffi. We've got a really exciting, kind of unique presentation that we're going to do today. I'll introduce our two presenters here in a second, Gary and Peter with us. I've known Peter for what, 30 years, I think, going back to RPA days and from solar projects in the past. To make a long story long, here we are, Peter and Gary. Now, I don't know Gary. I've never met him personally, but I know of his reputation through some other friends, through Larry Weingarten out there in California and stuff. And this is a great team. You're going to learn a lot from this presentation. They have a lot of experience. They have a lot of hands-on experience with the jobs that they work on. They don't just design and send out drawings and lines and prints. They actually go to the jobs. They make sure they work. They take responsibility for them, which is unusual in this day and age when stuff is being generated overseas and you get a file sent through your computer and that's all you get for a design. These are fellows that really take responsibility for their designs, and they push the edge a little bit. They're trying to find better ways of doing what we've been doing for years, and I'll let them explain more about that. So I don't know if you want to talk about this slide anymore, Peter. You want to move on, Gary?
Yeah, let me just say for both of us how grateful we are that Caleffi has given us a chance and such a grand stage, to talk about where we're going with this revolution in pipe sizes and better designs overall for plumbing. A design that Gary and I have been talking about as practically perfect plumbing. We hope that people really get it, that we have a really good news story to tell you today. It's a win-win for everybody, the installer, the plumber, the designer, the owner, and the tenants. They all benefit from a better design plumbing system. We work in the net zero realm a great deal, and that forces us to focus on making small beautiful, and in so doing, save water, save energy, and also make sure that the tenants get the kind of service from their hot water system and cold water system that they deserve and they pay for. So Gary, you might have a few notes you want to say before we get into the real nitty-gritty of plumbing.
All right. Thank you for the opportunity, Bob. This is a great place to share the ideas that we've been working on and the practice that we've been trying to implement. And so let's just get started.
Okay. Yeah, thanks for joining us with this and putting this together. I know it was a bit of work to squeeze it down into an hour, and we've got a lot to put in there. So here you go.
You mean we don't have a day? This isn't an all-day presentation? Did I miss that memo?
Well, I'll start at the beginning, and the way we're going to do this is Gary and I talk almost every day for long periods of time. My partner says he's my new boyfriend, but anyway, we did start at the beginning about, was it 2 years ago, when I finished my first what can I call it, kind of demonstration of what Gary's been talking about for 20 years. I happened to run into one of his presentations online, and it looked good to me. He was talking about trunk and branch and twig. Well, I grew up in Vermont, so that all sounded really good because I used to tap trees and make maple syrup. I kind of like that, right? And I wanted to go small for my net zero clients, and he talked about home run 3/8 inch twigs, and I said, let's do it. The GC said, oh, all right. You crunched the numbers, I crunched the numbers. It looked like it would work, and we put it in, and it was a great success. And we and this project went on. It's called Net Zero Village. Is now a new one that we're working on called Solara. And the design that Gary really pioneered, I actually put in practice, and it works just great. And it doesn't involve 2-inch pipes to carry 3 gallons of water. And our goal is really making the tenants happy, getting them that hot water fast, not wasting much of it, and keeping energy losses to a minimum. Gary?
Yes, thank you. So we have these topics. You can see them all. We'll do our best to get to the finish line today. And why don't we just go to the next slide?
All right.
So begin at the beginning. We've described here a process of thinking about how to I guess, how to rethink the way we do plumbing design. Pete was fortunate enough to not be steeped in code, but he started designing for Solara. He's an engineer, and he went back to first principles and said, well, let's just do the math and see what the math says. And then he got an opportunity to look at real flow rates and figured out that, why is there a 3-inch pipe in these buildings I'm working on when I only see peak flows of a few gallons a minute? It made no sense. And so we've been working on this process of how do you think about plumbing together for a little over 1.5 years, almost 2 years now. When I think about begin at the beginning, I actually want us to start our design work at the apartments, the fixtures in the apartments, and work backwards to the service entrance of the building. Because the tenants are who we're trying to provide hot and cold water for, not the building, not the mechanical room, but the tenants. And so we're going to talk about our experiences looking at a few apartments, buildings in upstate New York. Let's go on to the next thing.
One point I want to make is, and you'll hear me talk over and over again, is when you're done, you really need to stress test the system. And as Gary points out, what apartment did I go to for that stress test? I went to the last apartment on the trunk line, because if it doesn't work there, we got a problem. So we try to design for that last apartment on the trunk, and the rest is gravy if it works.
I think that our industry is starting to call that stuff the most hydraulically remote apartment.
Okay.
So on this one, what's the goal, Pete? What are we aiming for?
Well, we want happy owners. That's really important. They pay us and they expect everything to work. They don't want to pay a lot for the installation if they can pay less. They don't want O&M problems. They don't want hot water complaints from the tenants, and they want clean water, because clean water means safe tenants. What do the tenants want? They want hot water, always hot and free of contaminants. They want it to get there quick, and they want it to come out with enough pressure. Even those at the end of the network, us designers, well, we want happy clients. We don't want embarrassments with O&M problems, and we got to have safe water quality. What does the world want these days? They don't want to stop waste of water, and they don't want energy to be wasted inside, because any energy that these networks dump into the interior of a building has to be taken out during the summertime by the heating system. So it's like a radiator. You got to insulate. Boy, I didn't even realize it was so important until after Meadows. And when we tell you the Meadows story, you'll certainly agree, I hope.
So I look at this as a case of what we're aiming for is providing hot and cold water. And most of our talk today is going to be on the hot water side of things, because it's a lot more fun and interesting. But we're providing hot water to the tenants at their apartment. And so they need somewhere between, I don't know, 15 and 25 gallons per person per day. Who knows the exact number? It varies all over the place. But it's somewhere in that ballpark. It's not 50 gallons per person per day. It's typically on the order of 15 to 25. Pete's got some fun numbers to share with that. But everything else, getting the hot water to the fixtures in the apartments is a loss.
You had a good point, Gary, during the practice. You said that they don't design buildings for plumbing. They put the mechanic room at the far end of the building, as far away as possible from that last fixture. They just don't think about that when an architect or a designer designs a building. They don't think about the plumbing at all.
That's exactly right. I actually think that architects will lose their license if they put the mechanical room nearer the furthest fixtures. I think it's a requirement that they put it diagonally opposite an elevation as well. Why? Because that's all we see. I know there's reasons. I'm being silly to make the point, but yeah, our purpose is to deliver the hot water to the tenant, and everything else is a loss in the system. And I think we have to convert our conversation to that. So Pete, what did you do during the COVID lockdown?
Well, I sat in this room with my Monet behind me, either on Zoom calls or spending time
Sure.
talking to my partner or looking out the window. But I was lucky enough because I was an essential worker at the Solara buildings. I was expected to get my work done. So part of the day, usually in the evening, when the rest of the trades had left, I went there to put in pipe and to put in tanks and do the things that I normally do for solar thermal installations, and to also make sure that any plumbing that went in met the design expectations and specifications that I created. Thanks in part to you, Gary.
Well, then we got a call from the folks at
Yeah, yeah. Paul, who's on this call. Hi, Paul. Wanted to see what we did at Solara because he was working on a second phase of buildings that, by the way, I had had a lot to do with installing solar thermal systems in the first phase. So getting Paul to come out and see Solara was a great honor because he runs a business with a lot of low and medium income buildings around New York and other states. So I showed him what we did and why it worked, and then followed up with him to see if he might be interested in letting us look at the design for the plumbing systems in their next phase. 3 buildings out near Utica, just up the road from John Sigenthaler. One of these days, John's going to come and look at this thing. But anyway, it's very audacious of us to suggest to Paul that he change the plumbing system that he has a plumber under contract to build. But wow, what the heck? It was COVID. I was locked down. Let's go forward. So that's what we did. Paul allowed us to make a presentation, and the rest is history. Right, Gary?
Yes, that's right. Thank you, Paul. So let's move on. So we've pretty much covered much of this slide, right?
But we were lucky because Paul wanted a peer reviewer, and that really gave us a chance to not only explain the benefits and challenges of a better design, but also get the kind of engineering peer review. John MacArthur was just great. He looked at every little thing, and as a result, we got a much better proposal to Beacon. And the plumbing contractor, they said, yeah, I've been wondering how come you guys have such big pipes. They were like 2.5 inches, and we'll show you what they look like. And this was our challenge, was to replace something very complicated with big pipes with something very small and more efficient.
So we have a poll question here, Bob. And while you're taking the poll, the apartment building is a seniors complex, 1 bathroom in each apartment, 1 washing machine per floor. There's 3 floors. What do you think the actual peak flow rate would be?
All right, yeah, we'll give people 40 seconds or so here to come up with an answer for that. I think we've got a lot of plumbers on here that are probably experienced in this type of, or this size of a project and this type of building. So I imagine we'll have a broad range of answers to this question, but it's a good question to ask because that's, like you say, you got to start at the beginning. What kind of, water flow do we need for this building? If you don't have that answer, then everything else is kind of a moot point as far as designing and selecting pipe sizes and pumps and everything else that go in the building. So let's see what we have. We'll get a couple more seconds to run, but yeah, good job, guys. This is an interesting topic, and we might have a follow-up with Pete and Gary on pressure because that comes into play with this building design also. But first things first here. So what do we come up with for the poll?
Okay, a great range. So about 20% think it might be less than 10 gallons a minute. The bulk of everybody thinks it's somewhere between 10 and 50, and more than 50, 14%. Well, we're going to cover the answer to this question as part of the conversation today to give you a range of what it is we've designed for and found. Okay. So very exciting. This is great. Let's move on.
Well, one of the basic
box.
Yeah, one of the basic ingredients I used for all my plumbing designs at the Net Zero Village and at Solara were based on data that I collected using a Flexum Fluxus ultrasonic flow meter. You see it in a picture down there in the lower right-hand corner. And that device really has been a godsend to me because I needed to build my solar thermal systems to match the load. Putting in too large a solar thermal system yields stagnation, breakdown, all kinds of O&M issues. So you want to right size your solar system. And the only way to do that is to figure out how much the load is. And you do that by measuring it. Most plumbers can't afford a device like this, but one of my clients couldn't afford to pay me, but he had one of these lying around. So I got it, and it's been a godsend for the last 6, 7, 8 years. And all these data that I collected suggested much lower flows than I later understood were predicted by what is called the water service fixture unit approach. And the codes talk about that. Gary's talked about that for decades as being outmoded. And wow, I'm glad I didn't know it, because if I did, I would have thought my designs, small as they were, couldn't possibly be right. But I had hard data. But when Paul saw my data and some of the frequency analyses that my son did with statistics, I don't think he really believed it. And he had every right not to believe it, because it really ran counter to the expectations of the engineering community. And so with the help of Frank McClenahan and others at NYSERDA, we were able to afford a better unit. And you see Hugh Henderson, who lives out near Syracuse and is a tremendous force in the monitoring community for New York. He created what I call a magic box, and it has 4 ultrasonic flow meters, sites, NIST temperature sensors. It's got a communication capability and a data cache and an automatic statistics generator. We are so blessed to have that, and have Hugh's decades of experience. Anyway, and so I would put together these schematics you see on the right, and he would come up with the math and then deliver, after 2 days, 5 days, 10 days of data, some wonderful statistics. Now we have the data to show Paul and any other client that the numbers predicted by the guidance out there, the engineering guidance, just would lead to an oversized system. And our systems, based on first principles, would work just fine. And then we had John MacArthur, kick our tires and make sure that we weren't completely out of our minds. So here's some data that Hugh's Magic Box created in Building E, which is a phase 1 building at Meadows that they already built. Senior housing. Take a look at these data. This is the hourly data. This is the maximum use, and we're really talking in gallons per minute. Look at these numbers, folks. Look at these numbers. The black line is the average during that hour of the day. The dotted line, or the dashed line, is the maximum. Take a look at that, 1.75 gallons. Oh my gosh. And then the blue line are the standard deviations. And the maximum hour for this building was 106 gallons. Really, this isn't what the water service fixture unit approach predicts. Next one. So here on the left-hand side is the cumulative frequency analysis that my son Willie put together. Flow rate on the bottom, the frequency of its occurrence on the left-hand side. Hot water is the brown, cold water is the blue. I'm sorry, you can't see it down there, but the maximum we identified at Building E is 2.85 gallons per minute at a 99% return frequency. That's only 3 gallons a minute for this particular site. And it was weeks of data. that are represented there. Now,
And the,
I
the
don't want to
the
mix.
the cold looks like it's only almost 5 gallons per minute in the 99th percentile.
Yeah,
Right.
yeah. I haven't
And the
studied cold.
the WSFU method is based on a 99th percentile calculation. That's what Hunter did way back when, and it formed the basis of all the math that we live with today. And what we're seeing here is that the 99th percentiles for cold are less than 5, and the hot is less than 3.
So if you look in the
Very low.
lower left-hand corner at the histogram for one of our Solara buildings, that's at full occupancy, maybe 38 people living there. There, our maximum flow was 4.2. And, you know, it's about the same number of tenants, more apartments, but a different group of people. And this is during the lockdown. People weren't going out. It's only 4 gallons a minute at 99%. This isn't a lot, and that's why our designs actually work. Go ahead, Gary.
Yeah, so it turns out that the number of people matter, not the number of apartments, although one might be a predictor of the other. And so one of the issues is really knowing your occupancy, right? If you've got special requirements in an occupancy for requirements of filling up lots of bodies in an apartment building because of the tax implications of the way you build your building, then you have to plan for the number of people. But I'll give you a clue. If there's only one bathroom, there's no simultaneity between bathrooms in your apartment. And so yes, people drive the total volume, but the number of fixtures drives the potential for simultaneity. So here's the original design for building for the buildings at Meadows. I think we'd like to call this the rib cage system. There's a spine of plumbing that runs up to the attic, and the third floor goes across the long corridor, and there's branches that come down past each of the mechanical closets on the first, second, and third floors, and then there's a common return based in the ceiling of the first floor. That's the blue line running down the middle. There's a separate zone right above the mechanical room. There's 5 apartments on that side of the building, and they're served separately, in this case, off of basically a branch off of the initial trunk. So that's the basic design. And we analyzed the feet of pipe in the building. We had good engineering drawings. The plumber was pretty much convinced they built it roughly like the plans had said. We don't have as-built, but it's probably pretty close. And we used this to analyze the existing design for the building. Right, Pete?
We did. But before you go on to our design, which I think you'll see is so much simpler, could you, Gary, just go back to that important word you use, simultaneity and flows? You know, we're trying to move all the people who are listening and in the engineering community toward more modern views of flow rates and more modern views of simultaneity. That's really important. Can you do your magic on that?
That was an album by the Police, wasn't it?
Yeah, right. Might have been, yeah. So look, the building if there's 35 bathrooms, there's a potential for 35 showers to be on at the same time. That's right, it's possible. And if each shower is a couple gallons a minute, that'd be 70 gallons a minute of peak flow for the whole building. Well, we've got data from single family dwellings and from apartment buildings now that has been used to create probability curves, just like Hunter did way back when, for modern buildings with modern flow rates. And the simultaneity is significantly smaller than anyone would guess. In an unrelated project to this, a friend of ours, Carl Hiller, did a research project on some hotels, and the hotels, 100 units in the hotel room, the peak number of showers operating at any one time was between 10 and 15 on the busiest day of their year. And it didn't matter whether it was a conference hotel or one along the freeway. We did both. The key is that the bedroom wings act like bedroom wings. and there's only one bathroom in each hotel room. So there's only so much simultaneity that can happen, and it's much, much less than anyone would estimate. And the simultaneity carries through. If you're on a branch, you can be simultaneous with things on the branch, but not simultaneous with things on another branch. You just have to plan the plumbing accordingly. So here's our design that we came up with. We have still a long spine of plumbing, but we now have 2 separate zones, and each zone has its own pump. We got rid of all of the balancing valves and all of the difficulty of balancing. I'm sorry, Bob, we didn't need all that product from you, but there you go. But we did use the Caleffi mixing valve because it had the capability of running correctly at the lowest flow rates that we thought we'd have in this building, because we were needing fairly small circulation pumps because we have such simple plumbing. And so we have the main loop. It goes out along the ceiling of the first floor up to the 3rd floor ceiling and comes back along the 3rd floor ceiling. Right there, just before that, where it switches, that's the hydraulically most remote branches, those 2 apartments. And then the return begins and goes back down to the mechanical room. There's a completely separate zone for the 5 apartments that are above the mechanical room. And there's a small circulator pump on each of the 2 zones. That's how we structured the plumbing. And we were able to change pipe diameters based on the calculations we did. We'll come to that in a minute, such that we kept the time to tap for the apartments equal to or less than the original design had. So it wasn't perfect from our point of view, but it was as good as we were able to get this first time out. Let's move on. There we go. So I hope some of you have heard about the water demand calculator. It was developed by IATMO as part of the WeStand process that they have been undergoing for half a dozen years now. It's used for estimating peak water demand for indoor residential use. It applies to single family dwellings, apartments, and to multifamily dwellings. And you can download the calculator itself in Excel, and it turns out just this past week it came available for your mobile device. It's real slick. As you can see, there's a list of fixtures on the left, and there's a column that's probability in blue. The probabilities are worked out by the people who developed the calculator based on real data from real buildings, real dwellings. And then you get to put in how many fixtures of what type you have and the peak flow rate. And so you can't go higher than what the program allows. It's designed for people who are building water efficient dwellings. It's not designed for the old fixtures, but it works. And since Pete and I are working on projects with generally water efficient fixtures, it works fine.
So
right?
Does this replace the Hunter's curve? I see the Hunter's number is still over here that you can put something in, or what?
Oh, it actually calculates the Hunter's number. So it's the exact same method that Hunter used back in the 20s and 30s and published in the 40s, with minor modifications, but it's essentially the Hunter's method. And it creates a different way of calculating the peak flow rate. And then you take the peak flow rate and go into the engineer's appendix in either the IPC or the UPC to determine the rest of the pipe sizing. So instead of using WSFUs and counting them and then looking it up in the table that says, here's how many WSFUs equals how many gallons per minute, you get to the gallons per minute using real flow rates and realistic probabilities for modern fixtures that we find in our buildings. And it gives us a much closer to reality number than we find in the WSFU methods in either of the codes. It's pretty slick. And we use this when it came out, and you'll see it here in this slide. Here's an example of a couple of different buildings in different parts of the country to see what it does. The buildings we worked on are in Utica, and I worked on some project in Seattle, and we'll show the comparison. So you can see the number of units, the number of bathrooms, the number of clothes washers, right? And we used all of that in the calculation. Seattle's based on the Uniform Plumbing Code. Utica is based on the International Plumbing Code. And Appendix A or E allow you to do the calculations just straight up, right? Fixture by fixture, and you do your WSFU count accordingly. Both the IPC and the UPC have a bathroom groups modifier that you can take into account. And so let's just stay with Utica. So the Appendix A says you need 80 gallons a minute or a 3-inch pipe and a 3-inch pipe coming into the building. That's what was built on the buildings, the first three buildings on the Meadows site. And if you take into account the bathroom groups, you get 70 gallons per minute, and you still need a 3-inch pipe. Okay, that's what the code says, and that's how the calculations were done for Meadows. So still a 3-inch pipe, somewhere between 70 and 80 gallons a minute is the expected peak flow rate. Version 1.4 of the water demand calculator came up with about 16 gallons a minute and the need for a 1 1/4 inch pipe. That was available when we designed the building, and that's what we went with as our proposal. And then the water demand calculator version 2, which just came out this year, says, nah, that's too high. It's really closer to 10 gallons a minute, and you need a 1-inch pipe. Nobody on this call would expect to see a 1-inch pipe in a 35-unit apartment building. Me either. I think it's way too small. But the physics says it's likely to be all you need. Well, actually, Pete's gone and measured it, and we've never seen more than 5 gallons per minute coming in on the cold side. Not once, not ever, whenever we've gone out there to measure. So that's a safety factor of 2 to 1. Maybe we only need a 3/4 inch main for the whole building. What do you think, Bob?
What do you think, Paul?
So, I mean, that's what it's so striking. One day, John MacArthur got a call from the water district and said, how come you only need a 1 1/4 inch main for this building? It's a 35-unit apartment building. We always put in 3-inch mains. In fact, they're right next door. There are 3 buildings on the site, and you want me to go to this size? They spent an hour or so going over it and figured out that the math was fine, and they put in the smaller meter. That costs more, right? No, it costs less, right?
Well,
all of the equipment in the...
Gary, we'll talk more about costs, but
Right.
please just mention the Seattle pricing for installations. This is a killer. I can't believe it.
Yeah, go to the next slide. What does it cost? Right? So this is for Meadows. Look, what we got rid of all the fat pipe, right? And it costs more per foot, and it's harder to install. It costs more to insulate. This is just showing you the difference in the piping costs between the original layout and the revised layout that got built in 3 buildings at Meadows. That's like what, over $5,000 difference in price just in the piping? We're missing the fittings and fasteners, the insulation, the equipment and mechanical room, slight difference in labor, and the cost of the water meter. We worked out the math on this project, and it's on the order of $500 per apartment was reduced in cost, was the reduced cost. Now, I know that people debate $5 up or down a lot, and we're talking about a huge difference in first cost, as well as running costs, right? Your meter charges are less per month because you have a smaller meter. So at a minimum, you save in the water costs. It's pretty amazing. Okay, Pete, you take this one.
Yeah, just to make Paul feel better and actually me to feel better, you know, we were talking about 35 apartments, and we wanted to make sure that actually on the main loop, we really only had 30 apartments, but I just wanted to make sure we weren't completely crazy. So I went out and I bought a whole bunch of 1-inch PEX pipe and a whole bunch of Viega fittings to mimic the T's and the other fittings that you would see, elbows and the like. And there's Trevor. Trevor and I laid this thing out. This is the same size as as what we're going to put in. And we put in pressure gauges along the way. We ran as much flow as we could get out of our pump through the unit, and by the way, much more than the 3-gallon maximum flow that we had measured in the earlier buildings. And the pressures were fine. They met more or less what Gary had calculated. So I could go back to Paul and John and say, we mocked it up, we ran it, and it's running just fine. And you don't have to worry that we're off our rockers, so to speak.
It's, we're practical engineering types. We like to make sure that it works. Theory's all well and good, but I want to see it function. And so we ran this experiment. And in fact, Pete and Trevor are out there on the jobs on the parking lot taking measurements, and I'm the data logger recording the numbers that Trevor yells out over the phone. I'm in California, right? So we did it the old-fashioned way, brute forced, and just measured stuff. And each apartment, according to the water demand calculator, ends up estimating a need for only about 3.5 gallons per minute, either hot or cold. And so we ran that on that last branch, right? We're stress testing this thing. So we said, all right, let's assume it's peaky, even though we doubt that to be true, but we'll run it. And then we added flow rates across the rest of the system to increase the pressure drop, and everything still worked. And so we ran it up to pretty close to what we expected the peak for the whole building to be. And as Pete has kept saying, we've never seen numbers that get close to the 10 gallons a minute that's part of the system is supposed to be able to carry. Just never gotten that close.
So when we proposed home run twigs to fixtures, 3/8 inch diameter, that's where we started getting some pushback from the plumber. He really liked the trunk and branch approach. You go out with 1/2 inch line, and then you put in a T, and then you run separate runs to each fixture. So I didn't know how to argue with him. He'd put in a lot more than I'd ever put in. But we agreed, what we're going to do? We're going to have a PEX challenge. And we would take 2 identical apartments, and he'd do it one way, and then he'd go over and he'd do it our way. And we timed him. I have videos of it. And you know what happened? It took the same amount of time. One thing we learned about any of this was the time it takes to hook up the Talon type, what do you call them? The hangers. Yeah, fasteners. You swing the hammer in the trusses, and it hits the truss cord, and then it hits the brace, and then it hits your finger, and you have to move the step ladder every time. Pulling these home run twigs takes like 5 minutes for all of them, and the rest of the time is moving your step ladder and trying to affix it to various points along the way. I think we can do better than that. If I had time, I'd like to work on that particular challenge. But in the end, everybody had to agree it took just the same amount of time, and the home run twigs get the water there with less waste, and in many cases faster. So that's why we're very comfortable in this particular case with home run twigs. It's not always the panacea, but it's a great way to go.
So before we leave this slide, if you look carefully at the manifold, you will see that the first blue pipe, the one to the left, is actually fatter than the other ones. That's for the toilet. And it turns out that flow rates of toilets are not the flush volume, but the fill rate. And at 3/8 tubing, 3 gallons a minute has a huge pressure drop in that segment of the plumbing. And so rather than suffer that pressure drop, because again, the buildings don't have to suffer that, we recommended putting in 1/2 inch tubing for the high flow rate toilet. It's a low volume flush, but the fill rate's not directly related to that. And so we got rid of a bunch of noise by using a slightly bigger pipe. No big deal. Keep going.
Okay, so the next one is the pièce de résistance. This is what I did in January and February. I got in a car, drove from Albany out to Utica over and over as we resolved better protocols, got better measurements, tools, and evaluated perplexing, what can I call it? Things we saw. So what you see here is what happens along the length of the trunk to the last the last apartment.
To
Yeah,
the last apartment.
number 303. Now the top line is the cold water pressure going into the hot water tanks. Down on the bottom is 0 to 13 gallons a minute. We had a lot of pressure to work with, and so we could force a lot of water through by opening more and more and more and more upstream from that apartment fixtures. And then we really nailed it with the janitor closets where we could get a lot of water. But anyway, you see down in the bottom blue line is the pressure at the wand for the shower nozzle. Now you say, oh my gosh, they lost a lot of pressure there. But look to the left where you see the pressure. We still had 35 PSI to drive that nozzle. Look over at the matrix on the right. We had 1.28, 1.26, 1.18 gallons a minute coming out of that nozzle, even though the hot water draws, I increased them over and over as I went to other rooms upstream to take more water out. More water than we ever measured coming out by other draws in building E. And yet over on the far right of that matrix, still 35 PSI left to drive water out of the nozzle. Now you might ask, why did you only get like 1.2 gallons a minute coming out of the nozzle? Well, those of you who've really looked carefully will open up a shower nozzle and you'll see this pressure compensating disc. And that disc determines how much water comes out of the nozzle largely, especially when you got extra pressure like we did. Now, if you're Pete and you rent a place like that, I'd unscrew that nozzle and I'd put a nicer nozzle in there with multi-functions so I could get all kinds of nice feelings out of it. But I don't think the seniors there will likely do that. And they'll be happy because they do have a consistent flow, even if their neighbors up the corridor take water out. And you can see that the pressure here on the lower line does not diminish very much, even though we take more and more water out. But you will also notice up there at the top, we have less and less pressure to work with because the pressure reducing valve keeps taking a bigger bite. We screwed it up to about 65 PSI, but look at it go down. So I asked Hot Rod, how come it's taking away pressure before we've even had fun with the water? Anyway, that's a separate thing.
We'll get to that.
So before we leave this one, you can see, as Pete pointed out, that in the bottom line on the left graph, the one for the wand, there's a big steep drop as you turn on the tap. That's coming from two pieces in the puzzle, actually three. There's pressure drop from the manifold to the shower valve because of the piping that we selected. We planned for that. There's pressure drop in the shower valve itself. We planned for that. And then there's pressure drop in the shower head of the wand. We didn't plan for that one. It was built in. We just didn't know what that number was. And so it is our suspicion that different wands have different pressure drops, and we ought to be always trying to find those that have the least pressure drop so you get the most flow. The flow rate of the wand was predetermined, right? That was picked by the specifier.
Just as a point, when I first one in building one at Solara, I thought I'd really covered the waterfront with all my mock-ups and testing and everything. We turned on the water a day before the tenants moved in, and the water coming out of the shower heads was terrible. It was wimpy, and oh my God, everybody's freaking out. Oh, it's all your fault because you didn't these home run twigs were too crazy. And I said, boy, I did all the calculations. Well, come to find out, the problem wasn't in my stuff. It was in the shower valve I had nothing to do with. Boy, that was a mistake. I should have followed all the way through and told the plumber to spec a different valve. That yielded a great outcome because Gary went out to Arcata and he tested a whole bunch of shower valves. And guess what? The one at Solara was the worst one. We were able to finesse it with different pressure compensating discs. But boy, that was a hard day for me.
So we'll cover that when we get together on the pressure talk sometime soon, Bob.
Yeah.
So,
okay, we also wanted to prove that the water got to these people fast. Nobody wants to stand there and wait for the cold water to run out and the hot water to arrive. So what we did, Trevor and I went out there with these very fast acting, meat probes and stuck it in the water and used my video camera on the cell phone to get a time-stamped video of arrival times. And that graph shows you one of them. It shows that in this particular case, 10 seconds for the arrival of the first water. And then it took 16 seconds to get up to 100 degrees. Well, I argue that for a sink, people are really happy to have the water start getting warm. That'll be a satisfied tenant. Yeah, they're happy. It's nice and warm when they're rinsing a dish, but when they're rinsing their hands, if it's warm at all, they're happy. And this is a first draw for the apartment. Let me tell you, it gets there real quick if it's a second draw because the manifold is nice and warm already. So but Gary feels a little differently because he thinks the water ought to be warm and he counts it from the time it gets to 100 degrees. So, but we're running out of time to argue about these.
So it turns out that the first rise in temperature actually tells you the volume in the pipe. And our research that's been done 20 years ago indicates very clearly that it takes roughly 1.5 to 2.5 times the volume in the pipe before hot water 105F or warmer reaches the other end of that pipe. It's true for all the pipes we've measured. It's certainly true for all the small stuff. And this graph is very indicative of what research has shown. It's great. Theory and practice. I love it.
So I'm just going to say,
pipe insulation.
Yeah, pipe insulation, insulate, make sure the butt ends are taped or glued because we just lose so much heat out of any little hole. And part of the inspection that I did during installation was to identify the actual installation of the insulation. But one of the problems was the sheet rockers were in a big hurry. And if the insulator didn't get there on time, there was a risk that these wouldn't get insulated. So that's a really important thing that the GC has to keep topmost in his mind. Get these insulated before these sheet rockers get there. Next.
And it looks like 1-inch wall on the hot line too.
Yep.
Yes. So the specification by the builder and by the code says you have to insulate all the hot water pipe. And so Pete got to take his magic box out and measure one of the buildings that had been built with the original design. And so we get the flow rate and the delta T running around the recirc loop, and we find out that it's large. It's so large that it turns out it was 50% bigger than the actual uses of hot water for the days we were measuring it. Now, that's a lot bigger than anyone would estimate. We all talk about hot water, recirc loops being 25, 30, 40% of the daily loads, which means they're less than the uses, right? And in this case, the losses were bigger than the uses by 50%. So we went back and did the calculation based on the design, and we found out that, oh, it looks like those pipes might not actually have been insulated, which sort of correlated with what we were seeing on the job site on the new buildings where the sheet rocker was running ahead of the team. And And so that kind of problem persists in a lot of construction, is that, you've got to decide what you're going to pay attention to. And if you want your pipes to be insulated, you have to give the time and the process to do it. And if they'd insulated it, it would have used less than the uses, but in fact, it currently used more. Next slide.
And also the recirculation pump is a lot bigger when you have to move this many BTUs just through the pipe to keep up with the.
Oh, yes, it was a big pump, relatively speaking. Yes. All right, next slide.
So in order to close the gap of issues that I wanted to make sure we had done right, I wanted to make sure that, in fact, it was insulated. Over on the left, you'll see the mix out temperature in blue. Look at it go up and down, up and down, up and down. That is due to the Legio mix hunting for our set point. I found that really interesting, and we had to move, thanks to Hot Rod told us to move our temperature sensor further away to allow mixing to take place. But anyway, if you look here, we ended up on the main loop of continuous operation with nobody else in the building at roughly 1.8, what did I say, 1.86 degree difference going in and coming out at 3 gallons a minute. Now, we don't pump it that fast normally, but at 3 gallons a minute, that's all we lost. I crunched the numbers and I came out with about 28 million BTUs per year. And, I was just delighted with that result. And keep going. Next slide. And the reason is, go ahead, Gary.
Go ahead. No, we in fact predicted it.
Because there you see on the lower right-hand corner, 29,787 BTUs lost a year. And so here we had real numbers matching estimated numbers. So I felt really good about that. And I'm convinced you got to insulate the pipes.
No, you're not supposed to. It's not allowed. Yes, you have to insulate the recirc loops, and you have to insulate the branches off the loops because they act like fins. They suck heat away from the loop.
And the last little item here, one of the things that is very different between Meadows and Solara. At Solara, I was old school. I figured you put in like a 2 gallon, 3 gallon a minute pump, and you suck all of the cooled water out and you shut the pump off and let it cool down. And and I guess it's now 30 minutes later, we turn it back on and do it again. That's not what got spec'd at Meadows. At Meadows, we have these Loara pumps. They're adjustable with a little dial on the side. And we found that the pump on the main loop was pumping only 0.5 gallon a minute. And the one at that 5 apartment loop was about 0.75 gallons a minute. So in order to keep that last apartment seeing warm water, a lot of the time that Loara pump has got to keep going to feed the losses, even at 1.86 degree difference. So, that might be another one. How should you pump recirc low and slow, or should you pulse it? Anyway, or something in between.
Well, and it depends on the mixing valve too, because they have minimums where they don't like to, they have to have a minimum to be able to regulate accurately. And that's why you went with the Legio mix, because you had that issue with the 1.25 inch valve that was spec'd in there, needed 5 gallons a minute to perform properly. So by going with the small Legio mix with these low circuit recirculation flows, the valve works, which you showed on the first slide. So
right. So we're going to have a conversation in the future about where did all the pressure go. We have lots to share. You can see on the left that Pete and I have been measuring in the picture. That's our lab up in Arcata. We actually have data now on 70 different combinations of pipe and fittings for 1/2 and 3/8 tubing with modern fittings. So, like copper is modern compared to what's in the tables. Tables are based on steel pipe and threaded and flange fittings, and I haven't seen that in domestic plumbing systems in like 50 years, 60 years. And so we've got pressure drops in the pipe. We've got some good stuff to show you about the pressure drop through different types of aerators and faucets and showers. As Pete mentioned, we've measured the pressure drop through a large number of shower valves that are sold at the price points put in multifamily buildings. And so we've got data to share in another presentation that we'd like to do with you all at some point in the future.
Okay. Yeah, so I can talk to this a little bit. So there's our electronic mixing valve, our Legio mix valve that we think the majority of these are sold just as a mixing valve, but they also have the anti-Legionella function in it where you can elevate the temperature of your loop if that's desirable or required by a code or required by the building owners or something like that. So you can see there's one that's piped in with the control right above. It's a nice compact little valve. It goes in quickly. And you can see some balancing valves on this, some competitor brand balancing valves on this system and temperature gauges, so you can see what's going on here.
So one of the things you might want to talk about is what we were chatting earlier, is that the size of the Legio mix is small relative to the pipe it's connected to.
Yeah, you want to size this valve by the flow rate, by the CV, and as you just learned through this entire presentation, the flow is a lot smaller than what you think it is. So even if the line size is 2-inch, you might get away with what would you have, a 3/4? I think you ended up with on that building, didn't you? A 3/4. Our
Yeah.
smallest Legio mix was more than enough to provide
I want
that
you to give me a 1/2-inch one next time. I need a smaller one.
Right. And yeah, and we're going to get to this, and we'll address all those questions why we lose so much pressure going through this as we start, the fall-off pressure as we start pulling more flow through that valve. And it's a physics problem. It's not something that we put in there on purpose to piss you guys off. So we'll get to that on another. I know we're running a little bit late, but we'll talk to that, and we'll show you why the Caleffi is the best at reducing that fall-off pressure because of the design of the valve and the mechanism inside, really. See what else we got here. Yeah, it's all about fall off pressure, and that's really, this valve should be sized on how much you're willing to accept for fall off pressure. We're showing here a 7 psi drop in pressure out at this, what is it, about 8 gallon a minute flow rate, 7 psi, and we've compared this to some of the competitors, and there's some that drop off a lot as you start going up in the flow, and it's the design of the valve is what it comes down to, and we do a good job of that. So what else?
Let's wrap it up here. So one of the questions that we have to pay attention to is that as an engineering team, we design something, right? We told you what we're aiming for. It's trying to have happy clients and happy customers of theirs. But what we design doesn't always get built. What gets built doesn't always get inspected and verified that it got built. Right? And then you end up with customers that scream at you at 2 in the morning because they don't get hot enough water. And none of us look good in that process. Or the hot water waste that we just showed on the BTU per hour, day, or year. That someone pays for the privilege of buildings not done particularly well. Yeah. And that's an air conditioning, that becomes an air conditioning load when you have that much recirc loss. So, well, that matters more where I live than where you guys live, because we get this thing called summer all year and you get winter half of it. So yeah. Losses are odd, but rarely do they reach the occupants. So Pete, plumbing revolution is here now, right?
And smaller pipes are in, fat ones are out. Practically perfect plumbing, is the new normal if we can convince others. That poll question shows that still a lot of you on this call believe that these buildings use a lot of water. And we have this magic box. We'd like to use it more. It costs a lot of money. And right now, I don't have it deployed anywhere. Let's talk. We can only benefit by getting better data and more defined data with statistics. So I wish every Legio mix valve that went out the door, Caleffi, was being sent out to a job that had this information. Because they say we need a 2-inch valve. We say, why do you need a 2-inch valve? Well, because that's what the valve that's in there. That's what the pipe size is. Said, no, you need a 3/4-inch valve. In your case, you say, so I'm going to go from a 2-inch pipe to a 3/4 valve. It just doesn't. But the numbers are the numbers, and now we've got the reality with the data logging. So how do you argue with that?
And for the last point on that slide, I want to suggest that we have to design our plumbing systems with the ability to put in equipment easily to allow for test and inspection.
Yeah, confirm it.
Verification, confirm. And the sooner we do that in our designs, the easier it will be for folks to come in after the fact. In fact, I build in the data monitoring equipment into the bid as a requirement for part of the warranty. Because if you can't see how the system is performing, none of us, from the beginning of the process to the end of the process, know what actually happened.
Yeah, if you're not testing, you're guessing is what they always say.
Yeah, so I really think we have to do it. Thank you, Bob. This is great.
Yeah, this has been great, and you timed it out pretty well there. I thought you guys were going to go a half hour long. So hats off to you. Hats off to Pete before the roof falls in on you there.
That's our next one.
All right.
So do we have any time for any questions? Did anything come in, or are we done for the day?
Any good questions? I got Max right here. He's been monitoring questions. If there's one or two, oh my gosh, one or two. There's like 100 questions. Which one do you like there? All right, so how can I convince my local code official to accept water demand method? Local code officials and local unions have pushed back hard on the demand method or anything other than what's in the book, basically.
Sounds like Chicago asked that question.
Union City, so.
Yeah, no, I get it. So it's, look, what we found is that by sharing the data with the inspector, with the engineering team, going out and measuring some flow rates in some real buildings will actually show them that the sizing methods are not crazy. It will be slow. Look, we know that. We were very fortunate to have a willing client, a willing engineer, and a willing set of plumber and inspectors. We got lucky. But the fastest way to the finish line is to not talk about the physics, but to demonstrate it with measurement. It's way faster, way less painful. Everyone looks at the numbers and say, okay.
Yeah, well, anybody that we didn't answer questions, we went through it, we'll certainly get back to, if we have to pass some of them on to Peter and Gary to answer the question properly or accurately, we'll certainly do that.
We'll happily do it. It's part of the deal.
Okay, anything else, Max? Let me see what I've got for housekeeping. So yeah, we got a podcast going. We got a lot going on. We've got Shop Talk. We've got Coffee with Caleffi. We've got a podcast. We've got Cody with his 5 things you should know. So there's no excuse for not getting information from Caleffi, however you want it, when you want to hear it, whether you want to see it, you want to hear it from another source like we had today. So it's not all coming out of our mouth. We try and involve as many people in the industry as we can on these webinars. So what else? Yeah, there's the 5 things to know. That's going to be a quickie. That's so if you don't want to spend an hour listening to us, Cody's going to give you some important information quickly in the 5 things you need to know. So that's kicking off 5 minutes. These are all the different social media places that you'll find us hanging out. We've got a contest going on right now, March Sadness, I call it, March Madness, I guess. Contest over on Instagram where you can win some prizes. So if you hang out there, if you want to go play the game with us, please go over to our Instagram site there and join in on the fun. And I think we did it, gentlemen. Thanks so much. This was great. I'm glad I stumbled across you and this information. I think it was through Larry Weingard, Gary, that he said, you got to talk to these guys. You got to get them on there to explain all this. This is crazy. So here it is for everybody.
Yes, thank you.
I just want to express my gratitude to you for all these years that I've called you up with probably the most elementary plumbing questions ever. And you've never, ever been irritated.
Well, there's no such thing, Pete, as a dumb question, usually. But
we should have a contest. We should have a contest for that, Bob, on the next webinar.
Yeah, there we go. All right. Any other questions? Anybody in Milwaukee or anywhere else that's from Caleffi have anything they want to add or ask or questions, Mark or Mary, Cody, anybody? Bueller, last chance.
Bravo, gentlemen. Thank you from Caleffi HQ in Milwaukee.
Well, and big thanks to Mary. She does puts all these slides together and makes them look pretty and make sure they're in order. And she's our editor, so to speak, of these Coffee with Caleffi. So thanks for all your help. I've been gone all week, so I just walked in yesterday and just stepped into place, and you made it easy for me. Thanks.
Thank you, Mary.
Thank you, Mary. It's been great.
All right, well, I think we're going to call it a wrap here.
Yeah. Yes, goodbye. I'm leaving.
Thanks, guys.
Thank you much. Bye now.
All right.